All right, guys. So, for this lesson titled Special Right Triangles 45, 45, 90, first of all, I promise this video is going to be a lot shorter than my previous one. I know my last one was kind of long. Everything you see in front of you are the only notes for today. Okay, so again, make sure you guys have all of this copied down before you actually continue with this video. The colors are not necessary. I did it as a visual to kind of help you guys out a little bit. But again, when you're taking your own personal notes, it is not mandatory that you include these colors, okay? So these special right triangles are called special for a reason, okay? Special because they include certain properties that help us solve for missing sides of these triangles, okay? Just to make this clear too, when we're working with special right triangles, all we're going to be doing is solving for the sides. We're not going to be solving for angles. I'm going to show you guys why in a quick second. Okay. Once I run you guys through this, you're going to realize there's really not a lot of solving. This is really a lot of just applying quick tricks and properties here. Okay. I'm going to actually do a little bit of solving to show you guys the properties and the tricks we'll be using. But then from there on out, it's kind of just applying these quick little tricks that we're going to learn. Okay. So our first case here is our 45, 45, 90. Now our 45, 45, 90 special right triangle actually forms from a square, right? We know the properties of squares, that all four sides are congruent, right? Hence the tick marks there. And then we also know that all four angles are 90 degrees. So if I were to take that square and actually cut it in half or draw on a diagonal here, all right, so I'm going to do this with the orange, what you end up doing is you end up forming a triangle right there. Okay, I actually took that and I redrew it over here. So I have that little 90-degree angle that got transferred over. I have my diagonal, and notice now I have two angles in there that are 45 degrees. Reason being, when I draw on that diagonal, the property of a square is that when I form a diagonal, I'm actually cutting that 90-degree angle into two smaller 45-degree angles. Okay, hence why we have a 45, 45, 90 right triangle there. Okay, you're going to notice that the two pink sides here, right, they form that 90-degree angle, okay, and they're both going to be considered our legs, right, a leg and a leg, and then we always know opposite my little box is what we call the hypotenuse, right? That's old information to us. Okay. Now something else that we can recall back from, I think it was Unit 2, anytime we have an isosceles triangle, we know two of the angles are the same, we know those two corresponding sides are also the same. So in this specific case, the two legs, leg and leg, it's not short leg or long leg, it's just literally leg and leg, or isosceles leg and isosceles leg, okay? Meaning these two legs are the exact same measurement. All right, so moving over here to my next diagram, I don't have it highlighted, okay? Again, I know that these two legs here, the leg and leg, are the same measurement, okay? So if I'm going to actually use a variable to describe this, whatever this leg is measured as x, some unknown number, this leg here is going to be the exact same measurement, okay? Now, technically, anytime we have a right triangle and we have two out of the three sides, we can use a special theorem to solve for my third side, right? You guys remember Pythagorean theorem? Okay, so if I go ahead and do that, so again, we know it's like my leg squared plus my leg squared equals my hypotenuse squared. Let's go ahead and see what happens when we do that, okay? So I'm going to have x squared plus x squared is equal to my hypotenuse squared. So I'm going to kind of derive what the hypotenuse is going to represent in terms of x right now. Okay, so if I combine 2x squareds, right, 1x squared plus 1x squared is going to give me 2x squared, and that's going to be equal to my hypotenuse squared. Okay, and then technically what I want to do is I want to get just the hypotenuse alone without that little exponent there. So what I'm going to be doing is to get rid of that exponent of 2, I have to go ahead and take the square root. So I'm taking the square root on this side, taking the square root on that side. Now technically what this means is that I'm taking the square root of 2x squared. And that's going to give me my hypotenuse. Okay, so if I actually want to find the square root of this, I can actually separate these two terms of 2 and x squared. So find the square root of 2 and the square root of x squared is equal to the hypotenuse. Hypotenuse. Now square root of 2, I can't simplify, right? So I'm just going to keep that as radical 2. But the square root of x squared, that exponent of 2 and the radical, those are opposite operations. So those technically cancel each other out. And I'm left with radical 2 times x is equal to the hypotenuse. Now how you guys are going to see this represented, instead of the radical 2 coming first, it's going to be the x first and then multiplied by the radical 2. That's going to be what the hypotenuse is equal to. So I'm going to put x radical 2 here. Now guys, all that really means that whatever the value is of your leg, to get the hypotenuse, all you have to do is multiply by root 2. That's it. Okay, so all this work I did right here, that's just showing you where this is coming from. You do not have to do this process every single time. All right, so how we're going to kind of show you guys is, you see how it says 2 cases. So case 1 is if they give you a special right triangle, 45, 45, 90, and they give you a leg, how can we solve for the other 2 sides? And case 2 is going to be, okay, they're actually going to give you the hypotenuse, and you have to work backwards and find the legs. Okay, so you really only have 2 options when working with the 45, 45, 90. All right, I apologize for that sound. It sounds like my dad's opening the garage right now. All right, anyway, so case 1, given a leg or an isosceles leg. So isosceles leg and leg are interchangeable terms here. On Mathia, they're going to be using isosceles leg a lot. So just kind of get familiar with that terminology. Okay. So if I look at my diagram here, again, if I know that one of my legs is 4, I know the other leg is also going to be 4, right? So I can simply fill in x as 4 centimeters. Okay. And then y. Now, y is my hypotenuse, and didn't we just say that the hypotenuse essentially is going to be the leg times radical 2? So if my leg is 4, my hypotenuse is just 4 root 2 centimeters. That's it. Okay. Now notice how it says equals and there's a blank space down there below. It says rounded to the nearest hundredth. So all that's saying is if I were to type in 4 root 2 into my calculator, okay, what is that going to give me rounded to the nearest hundredth? So meaning I can put in radical 2 in my calculator and hit times 4, and that's going to give me some number. I'm going to round to the second decimal place there. I'm going to hold off on doing that right now. I'm actually going to come back to that later because I don't have my calculator in front of me. Okay. So that's case 1. Okay, case 2 is now working backwards. So they're going to be giving me for case 2 the hypotenuse, which I have highlighted here in orange. They're saying, hey, figure out what the legs are. Now, if I went from getting from a leg to a hypotenuse, I had to multiply by radical 2. Now, they're giving me the opposite. They're giving me the hypotenuse and saying, hey, figure out the legs. I got to do the opposite of multiplying by radical 2, and I have to divide by radical 2. So think back to your notes, guys, when we did dividing. If I take 7 radical 2 and divide by radical 2, what happens to those radical 2's? They cancel out, right? So that means each leg, x and y, they're both just going to be 7 centimeters. Easy peasy, right? Okay. Now the special case, right, and again, you guys saw this with dividing as well, what if my hypotenuse is a whole number? So meaning, what if I have to do the hypotenuse of 8 divided by a radical 2? Now you guys know I can't just do 8 divided by radical 2 and say it's radical 4, or 8 divided by radical 2 is 4. We need to rationalize, right? Rationalize means multiplying both the top and the bottom by root 2. So root 2 times root 2 is just going to give me a whole number of 2, and then 8 times radical 2 gives me 8 radical 2. When I divide out the 8 and the 2, I get a 4. Oops. And then left over with a root 2. So that means each leg would be 4 root 2 centimeters. Okay, and if you're thinking to yourself, hey, well, miss, you showed us that shortcut, right, where I take the whole number of 8, I divide it by 2, so 8 divided by 2 is 4, and then just multiply by radical 2, so 4 times radical 2 is 4 radical 2. Guys, you can use that shortcut for this as well, okay? This is just me showing my work and showing you where I'm getting it from. All right, that's it for these notes here. Okay, you have case 1 and case 2. The practice problems you have, they're either going to be case 1 or case 2, okay? And it's just about applying your radical operations there. All right, nice job, guys.